All right, everyone. Um, Good morning. Like I said, we're going to be talking noise testing today. I feel like noise testing is a phrase that we throw around, especially us ABC folks. We've used a lot. You've probably heard us talk a lot about it, but not as many people know sort of what it is and how we go about conducting a noise test. So today I want to just walk everyone through sort of what it is, what we need to be aware about with it, how to conduct a noise test, and how to sort of interpret the data that we get from a noise test. And all of this to make a well-running Motus station and or maybe adjust some stations that are experiencing a lot of noise right now. So when we are figuring out the design phase and the actual installation phase of a lot of these Motus stations, there's a lot of qualities that we're looking for, and a checklist that we want to go through to make sure that we have a well-running Motus station. Some of the more obvious ones I think are better known by everyone are clear line of sight. We want these stations up at the highest topographical point so that it's not being blocked by mountains or by just other being in a low elevation spot. We want to make sure that the antennas are attached to a very solid structure that can withstand extreme conditions. We want there to be a reliable source of power for all these stations. We prefer them to be connected to Wi-Fi or cell data. We want those stations to be very accessible for maintenance purposes, and we want to have good relationships with our partners who are going to be hosting the station. So all of that stuff are things that I think are pretty well said through a lot of different Motus talks. But something that is more recently becoming more and more important, and something that we are still very much learning about, is having a station that has little to no radio noise interference, having what we consider a clean environment for our antennas to listen to. Because as something that we always want to kind of reiterate when we explain how these Motus stations work is these antennas are doing what's called passive listening, which means they themselves are not emitting something. They are throwing out this search radius. So when you look at the Motus map online and you see those ellipses, that is the search radius that these antennas are listening for. And we're listening for tags out on the environment. And so any sort of interference can hinder the ability for that station to do its job and for us to collect data properly. So when we are out looking, scouting a potential Motus site, we need to identify potential sources of noise. So what exactly is noise? Well, that is any electromagnetic or radio waves that are close to our 166.38 megahertz frequency. And you'll notice this is just for the 166, our low-tech tags. This is not something that we test for our ultra-high frequency, our UHF 434, which is the CTT tags. So this really is only applying to our 166 low-tech frequency, right? And so there's a bunch of different potential noise sources. That really common ones, and the ones that you would probably suspect that would interfere with our Motus station would be things like radio towers or cellular communication towers, other things that are emitting radio waves that are close to our 166. Usually when we're looking and scanning the horizon and it's littered with a lot of these cell towers, we know that's probably going to send back a bunch of noise. Another pretty noisy possibility is high voltage power lines. So again, this is not noise that we're hearing. These are different sources of noise and not necessarily just what you think of something that's sending an exact radio signal, but electronic electromagnetic waves. So high voltage power lines. These things are also going to throw in interference because they're going to be sending similar waves to 166. These are our big source sources of noise.
Or it's just like a presentation more.
Oh,
Oh,
someone's got
I'm
there.
sorry.
No, no worries, no worries. So these are like sort of our big sources of noise, but we also have several local sources of noise that we need to be aware of. Things like rooftop AC units are something that I feel like are very commonly encountered with rooftop installations. That is something that definitely emits local noise, so we want to try to get away as far away from those as possible. Even things such as a standard street light can emit just enough noise if you're close enough to it that can cause a problem. And especially electric transformers on power lines are something that can cause a problem. So maybe not our high voltage power lines, but even anything that is causing a problem. It can be a laundry facility, it can be just regular power lines. It really depends on the placement of your antennas, how close they are to that source, and then being able to identify that source of noise. Now, I'll go ahead and say that, if you are, especially if you're installing like an urban area, which I'm about to talk about, there are ways to mitigate receiving noise. There are ways that you can angle it away. Just because there is a noise source there does not mean it's inevitable that we can't use that station. There are different ways to angle our antennas away, move it as far away, get it around the other side of a building to kind of block that noise. So there are ways to mitigate those sources. So here's an example of up on top of a roof in Atlanta on the Georgia Tech campus that I was just at, where there's a Motus station, and kind of figuring out where we want to point our antennas. When we start to scan the horizon, of course, most of the time with our antennas, we generally have a direction that we want to send the antennas, but we want to, again, identify those potential noise sources. So when you scan the horizon, we can already start to see several different communication radio towers that can cause a problem. Those construction towers, that those can probably have some sort of radio communication system on them. That I had AC units behind me on the top of the building. So especially when you're in an urban environment, expect there to be some level of noise. It's more or less inevitable at that point. Is it a matter of, can we point it in the direction with the least amount of noise, with the least amount of interference? That's why we do like those stations out in the middle of nowhere, where there's fewer possibilities of getting noise. On the other hand, there's been several situations where we've gone and noise tested, and we cannot figure out where the source of the noise is coming from. It's probably something off in the distance that you just can't see. So sometimes it's a mystery, and that's why we do noise tests, because you can't always see what the source of noise is. And again, at the same time, I could be pointing it directly at those communication towers, and they could be completely fine. They might be emitting things that are way away from our frequencies, and they could be totally fine. So it really is a matter of figuring out the noise locally in comparison to our setup. And I just real quick want people to kind of understand how noise affects our abilities to detect tags at the station. So there's two main ways it's going to interfere with our tag detections. Again, if you're thinking about Motus, these tags are pretty weak signals across the landscape. So we're setting up these receivers to listen out for something weak across the landscape, which is already a difficult task at hand, right? And so one way that noise will interfere is if you have kind of this consistent background noise that may not be at a high decibel, but it's constant noise, something that is constantly flowing in. Adam likes to compare that to listening to a single raindrop in a rainstorm, right? You may not be overwhelmed with how loud that noise is, but you're going to reduce your tag detection rate because you're unable to pick out that single tag amongst all this other noise. The other problem that you run into with something that's causing very typically like very loud local noise, is that you're going to be producing false positive detections. So we've all probably seen those maps on the Motus site where the researcher has yet to clean the tag data, and you'll see a detection way, on the other side of the country that is just not true. Well, one possible reason for creating that false alias is that there is a noise source that is loud enough and consistent enough that it recreated those blips from a Motus tag in that with that ID. And so that's how we're able to. That's one way that false positives are detected. So those are the two things that we want to avoid. And so that's why we're going to try to set up as clean of a station as possible. And the way we do that is by noise testing. Noise testing is literally just being able to go out ahead of time and take a snapshot of what the local noise environment looks like. And what we're really trying to do is recreate the antenna setup that you're going to be building anyways, as close as possible so that we are replicating what will hopefully be that Motus station for the long term. So what we're going to do is we will have our noise testing kit and antenna, which I'm going to explain after this. We'll be using our noise testing kit. Like I said, we want to get as close to the proposed antenna site as possible. So if we're setting it up on a fire tower, I want to be pointing that antenna and placing and holding that antenna as close to where the actual antennas are going to go as possible. We want this to be at least 15 feet off the ground. So in this picture, Adam's holding it up on a fire tower that we were at in New Jersey. On a fire tower, it's easy to just go up to where you think you're going to be doing it and put it up. That's fine. Other times, you're going to be working on a station that you're putting up a pop-up tower, you're putting up a utility pole, so you're not able to actually reach that. Try to get creative in how you get up off the ground. We want to be a few standard wavelengths above the ground when we're using those antennas, because we want to make sure we're, again, replicating as close as possible. So if that means standing up on a car, one good way is to get an extendable painting pole and attach the antenna that way so that you can raise it up at least 15 feet off the ground. Any way to get it up high enough to where we're getting what will hopefully be a true signal comparative to what that antenna setup will be. And we want to record the environment for at least 10 minutes, preferably. If we can do 20 or 30 minutes. We know this isn't, if it was a perfect world, we'd set these noise testing kits up for a whole day, maybe even a week, to acquire the noise, because as we've found out, noise sources can come and go. It can be a daily fluctuation. It can be seasonal. I mean, if you're working in an area where there's a lot of, say, trucking operations, the noise is not something that's constant. It's something that might fluctuate. So the longer that we can test for, the better picture we can get in terms of, how is this Motus station gonna go. But we want preferably at least 10, probably 15 minutes of recording that noise from each direction to best understand, what the situation is. And the other part of all of this is that we'll have a test tag that is activated and placed relatively close by, so that we are figuring out how well our noise how much the noise is interfering with our ability to detect our test tag. And again, I'll kind of talk about that when I talk about the noise testing kit. Okay, so what is a noise testing kit? The short of it is that it's just a mobile sensor node. It's just a small sensor node that you're able to carry around with a portable 5-volt battery. This is something that's pretty easy to put together. Like I said, I've got a bunch of resources that I'll be sending out but one of these is just a video that Adam put together on how to build a sensor, a small sensor gnome that will be your noise testing kit. It's very simple. Just involves your battery, a waterproof case, bulkheads, and your Raspberry Pi, and sort of all the connections that go with a Raspberry Pi for a single antenna. It's relatively, all things considered, is pretty cheap to put together. And I know something that always comes up is, if we have a handful of noise testing kits that we pass around state to state to use, but we don't have a ton of them. So we encourage folks to, especially maybe agencies who are planning on testing for many stations over the next coming years, to maybe just put one together yourself. It's always nice to have that at hand so you can use it whenever you need to. Like I said, this video really puts it together really easily, and it has all of the on the video. It also has where you can links to get all of the equipment needed. So very easy resource to use. So there we go. We have our portable sensor gnome. It's a portable receiver that we're walking around with. And then we have the antennas that we want to use. We tend to use either 3-element or 5-element Yagi antennas. The only ones that we're going to recommend, you can find 166 Yagi antennas on Amazon. Do not purchase those. Those are not really reliable with the Motus network. We want to get ours from Intermod, formerly Maple Leaf, is a very reliable manufacturer. It's who we order our antennas from. We use 3 or 5-element mostly because, you're holding these up with your hand. You don't want to be lugging around a 9-element antenna with you. Obviously, that would be technically better for a noise test to get more accurate if you're planning on putting up a 9-element. But realistically, most of our noise sources are going to come more locally, and so 3-element and 5-element antennas. And I think 5-element, I would actually recommend 5-element more so than 3, just to give you a little bit more distance. We'll do a good job of figuring out, replicating that noise. The other thing is you'll need a short, maybe 6 to 10 foot coax, depending on if you're, running the antenna up a pole. You'll probably want 15, 20 foot coax cable. You can get a lot of pre-made coax antennas, coax cables with the N-type connectors, but we recommend that you use the LMR 400 coax cables. So that is the thick weatherproof coax cable that we use for installations. They make a lot of more thin coax cable that you can see there on the right. But those, like I said, those might be passing the information differently. And we want to, again, just replicate it as close to what the station will look like in the future, as close as possible. So that's our recommendations with using antennas in the coax. So you'll be able to hold up your antennas, plug it in with your coax, and plug into your mobile sensor station, or sensor gnome, excuse me. So that is essentially what the kit is made up of. It's very simple to put together, and all things considered, not too expensive. So the next part, that with your sensor gnome, you're going to make sure to have the version 2.1 now sensor gnome software installed onto your Raspberry Pi. And again, all of this is also on the Motus Wildlife Tracking Network YouTube page, which has several other videos that Adam has done about very easily flashing an SD card to make sure that you have the most updated version of the sensor gnome software. But this newest version is very easy to work with. It is quite literally, you turn on your sensor gnome and it will pop up as a Wi-Fi source, and so you'll just connect to that local Wi-Fi, and it'll walk you through sort of all of the different pages from there. So you just log in via Wi-Fi. You don't need to have an extra app. You don't need to do other things. It's just connecting it to Wi-Fi. And again, I'm not going to get into the nitty gritty of setting up that. Like I said, there's a couple videos that Adam put together that I'll send out and everyone can watch. So for our purposes, I'm just going to be showing sort of the important things that you're looking at with your interface here, right? So you're there, you got your sensor gnome on, you've logged in, and you are holding your antenna to the direction, and now you are recording that noise. So when we go into sort of the menu of our sensor gnome interface, the main thing we're interested in is the radios tab, because that's going to tell us everything that is connecting to our antenna, right? And sort of this on the right is sort of what it will look like. You will most likely only have one antenna plugged in. You are welcome to have two antennas. So if you have a couple people, you can be running two directions at one time. That's totally fine because you can differentiate between antenna 1 and antenna 2. Whatever your preference is, however you want to do that. But this is sort of what that interface is going to look like. You'll see at the top, it lists the number of radios that's connected to, and then it will have sort of this streaming table of pulses that will be coming in real time, and it will slowly just load as they are detected. And I'll kind of touch on what those mean. And so there's only a couple of things that we are really interested in. There's a lot of different graphs and gadgets, but there's really only a couple of things that we're interested in. The first thing is standard noise ratio, the SNR, the low-tech SNR. So this is where our test tag comes in. So again, we have our antennas pointing, we're running it, but we want to make sure that we have a test tag that is running nearby to, again, be able to compare to make sure, okay, can I detect a tag within this noise environment? And so we want to make sure that we take our test tag, it is activated, obviously, we want it to be running, and we'll have it maybe 100, 150 feet away. It depends on sort of where you're set up. And so the first thing you'll do is you'll adjust to make sure that you've got the right SNR. So you'll see those detections coming in of your test tag. You want to make sure that this is when I say test tag, it can be a tag that you have for another project, or there are going to be, hopefully in the future, rechargeable test tags that we can use to sort of always have on hand. We're still, figuring that part out, but it can be any tag that you have that you know the idea of, that you can just activate and have it running. One thing, these graphs that I record are actually not going to be very good quality graphs because the test tags I was using were in 30-second bursts. You want to use tags that are the 5-9 second bursts, something a little bit more frequent, so that's consistently sending something rather than really long periods between burst intervals. So my graphs are not going to look very good for these purposes, but I'll sort of explain what they should look like. So you have your test tag going, you're recording, and the value, you don't need to know too much about the SNR, except it's just the ratio of our tag compared to the noise around it. So we want that tag to be close enough that it's picking it up thoroughly, but not too close to where it's hindering our ability to measure noise properly. So we're going for an SMR of value between 10 and 15 decibels. So if it's lower than 10 decibels, we want to bring that tag closer. If it's getting higher than 15 decibels, that means the tag's too close, so maybe scoot it away. So put it in a place that hits that sweet spot somewhere between 10 and 15 decibels, and then we'll know, okay, our noise reading will be good to go. The next graphs will be our detections and our pulses. So again, this relates to our test tag, making sure that we're getting our test tag pulse correctly, making sure we're detecting it properly, making sure it's in a place that our antenna is actually picking it up properly. You'll see here in this middle graph, the low tech pulses. Again, I'm using a test tag that is actually I think it's 45 seconds. Every 45 seconds is when it's bursting. So it gives these peaks, but then goes down. So if we have a regular, 9 second test tag, that will give a more smooth line. So we want a smooth line, relatively smooth line, going depending on your pulse rate. So if it's every 9 seconds, we're going to have 1,600 pulses per hour. You do the math of there's 4 pulses per burst per 9 seconds, per hour. So whatever burst rate you have, figure out the math and figure out sort of what you want that value to be steady at for the entire time, rather than these weird peaks that my test tags was giving. Okay, so then once we know that our tag is sending out properly, we've got it at the right distance. Now we're just interested in the noise. So this is the information the most important information that we're going to be using. You can even do this without a test tag, which I'll explain in a minute. But we want to understand our background noise and our noise source. So the first thing is, if we again have our tag consistently going at the right SNR, we can use this low tech background noise graph. And again, it's going to probably fluctuate up and down, but it'll probably hit a range of decibels of whatever the background noise is. Ideal background noise level is going to be -70 to -100 decibels. So if we're reading all this noise, that's where we want it to be at. Remember, this is in the negatives, so you have to kind of reverse it in your mind. We want it to be a larger, 70 to a 100 because it's in the negative numbers. Once it starts going below, above -70, sorry, that's confusing. That's when we start to have more problems. We've had plenty of stations in the 65, 68 decibel range that is workable. But especially if it starts getting into the 50s or the 40s, we rarely see it get below that. If you get into the 30s or 20s, you have a serious problem. But once it even hits the -50s, that is noise that is going to be causing problems for sure. And we want to figure out a way to either move away from that, or that might just show that's not a suitable station. So again, we're using that graph, but you can also just visually monitor the noise based on the graph of incoming detections. So here we see on the right, you'll see our test tag come in. So it'll have one line that says tag, and each line is one sort of detection. So you'll see tag that has the tag ID that whatever test tag you're using. And then with it will come 4 blips. I think I highlighted one extra that's a source of noise. It will have those 4 bursts that are identified with it. And so what we're interested in, you'll see a couple of different values. The main thing we're interested in is that last number, in that last column. That is going to be our background noise level. That's where this low-tech background noise graph is getting its information from. So when we see that in the -80s and the -70s, that's perfect. That's exactly what we're looking for. That means it's low noise. It's nothing to really worry about. That's totally fine. Again, once it starts getting below 70, then we need to start thinking about how much it's interfering with us. The other thing that just evaluating this table will help us do is figure out other sources of noise that are just streaming in that may not pop up with our graph. So if we are seeing more than just every 9 seconds our tag and our 4 blips, we start to see other things come in, those are extra sources of noise, and we want to look at sort of that second to last value there, which for looking to the left of the red box here, are negative 59, that is the signal strength of our actual test tag. So if we see other things starting to come in that are not our test tag, those are other potential sources of noise. And again, we want to evaluate if it is constantly streaming in. And I've had several potential stations and even stations that I've installed, it turned out to be noisy using the 9-element antennas. It can constantly flow in, even when it's in the negative 70s, even negative 80s. If it is, 5, 10 detections a second, that's a problem. If it's flooding in like that. If it hits every 10 seconds, every 15 seconds, that's pretty normal. We'll almost always have something else that kind of comes in. If, again, it's very loud, if it's a strong signal in the negative 40s or 50s, we do want to be careful about that. But if it is a very infrequent blip in the negative 70s every 10, 20 seconds or a minute or whatever, that's totally fine. Like I said, it's almost inevitable that we are going to, have to deal with some level of noise. So very rarely do we get a perfect Motus station, especially in the Southeast where you have a bunch of small towns and cities and things like that. So again, just kind of to reiterate, the most important values that we're interested in here is that background noise being negative 70 or less, and also making sure there is not some flood of noise that's coming in as well. And so you can do this, excuse me, sorry. You can conduct a noise test without a test tag. I've done it plenty of times. If you do not have a test tag, you can't rely on the actual graph. You're just going to have to look at the table as noise comes in. Again, we want to use a test tag because we want to be able to compare and see how those tags are being picked up in the environment, and that will give us a better idea of that background noise. But otherwise, you can monitor that table, see what comes in, see the strength that those random sources of noise are coming in at. And that can give you a pretty good idea as well. So that's more or less noise testing. It's pretty straightforward. What we encourage people to do is, you run that antenna for, 10, 20, 30 minutes, depending on what you're able to do. And then you take screenshots of those graphs. You take a screenshot of the table of everything, and you make a note of which antenna and which direction you were facing it in. If you have sort of trouble still interpreting it, you're welcome to send it to myself or Adam or Todd if you're up in the Northeast, and we can kind of help you evaluate what that means. But otherwise, it's luckily a relatively straightforward process of just going out, using your noise testing kit, pointing it in the right direction, recording it, and taking screenshots, or just writing down what you're noticing. Screenshots are typically better just to make sure. Yeah, and then the other resources that I want to provide, like I said, there's the Motus Wildlife Tracking YouTube page that has several videos on there that Adam put together about making your sensor gnome, your mobile sensor gnome, and also how to set up your SD card with the most recent sensor gnome software. There is also the Motus sensor gnome user page, which also can help you set things up on the Motus website. Very easy to do. And then I will actually be sending out a noise testing document, a standard protocol that we've put together that, again, walks you through exactly what I just talked about today, that, again, highlighting the important things to record, the important things to take a screenshot of, and sort of the process of doing that. And you're welcome to, again, contact myself or Adam or Todd if you have any questions. We want this to be a standard practice for everyone to use. Yeah, so with that, I We'll stop sharing. We'll keep recording just in case we have any kind of questions that people want to ask. Yeah, so I'll open the floor to questions for anyone who has them.
Hey Garrett, can you hear me all right?
Yeah, go ahead.
Okay. Um, Hey, that was super helpful and super useful, and so I'm excited to start testing some of these stations in Tennessee. My question is, are you able, instead of a sensor gnome, use a sensor station? And is it just a matter of switching out the antennas from 166 to 434 to do the 434 interference testing?
Great questions. First question. Technically, you can use a sensor station, but what a sensor station is not going to do is it's not, you're using that sensor node interface through the sensor station, but that is not going to have sort of this newest sensor gnome software on it. So it's not going to have any of those graphs, and it's not going to have that SNR values if you're using that test tag. So you're really only going to be able to rely on looking at that incoming table, which, like I said, you can do, but it's what has been made with the sensor gnome software has been made it really easy to use with those graphs, and so we recommend doing it that way. The second question about the 434. So we don't test for 434 because there are very few things that are close to 434, and we
Okay.
you don't have the problem of false positives as like nearly as much at all, if at all, with 434. And so although there almost certainly is some sort of noise, we don't really know how to measure it properly, and it's not going to show up on any way to test it. Um, so that is something that maybe in the future we'll know how to do. But for now, we really just don't test for 434 because we don't deem it too necessary.
Great. That's great to know. Thanks.
Yeah. And also, I'll go ahead and add that it is nice to have a little sensor gnome in a small case too. It's a little bit easier than a bigger sensor station, but depends on what you're testing for. Are there any other questions from folks? Like I said, I'll be sending out sort of this information and the document that we've put together and everything else. But happy to answer any questions that folks have now.
I have one question
Yeah, go ahead.
about sources of interference that are within the detection range. Will you be able to detect them regardless of where they are in the detection field? Or for example, there might be a blind spot or something in the detection field at some point because it's so far away you aren't I don't know. The noise test isn't detecting it.
I see what you're saying. Yeah, and I've run into that problem. I was using a 3 element, which is not going to reach nearly as far. And then when I put up my actual station later, I thought it was clean. I put in my 9 element, and then all of a sudden, oh man, I've got noise. So, and also, like I said, it's also probably maybe just seasonally variable, or noise sources fluctuate over time. So it's not necessarily something that we can get the exact snapshot. The 10 minutes that we're recording our noise may not be exactly what it looks like throughout the year. So the one way, like I said, to mitigate that, if we're putting a station together, it's important to check the noise when you actually install the station as well. So you'll be able to look at that sensor gnome interface when you install your station and let it run for a little bit and check the noise. And if all of a sudden, man, I'm seeing a bunch of noise, maybe I need to adjust the antenna. I have very much fixed noise just even the slightest adjustment, especially of a 9-element antenna, because if you think about, how far it's beaming, just a little bit of moving it can get rid of the noise. I've done that several times. It's very possible, especially with one of these things where it's like, I didn't pick it up in the noise test with a 3-element and with a 9-element. That tells me, okay, it's probably not something local. It's probably a cell tower that I'm pointing at that I can't even see, 5 miles away. And so let me just turn it a little bit, and all of a sudden, that can fix the noise. So there's definitely ways to fix it if it pops up after you've, installed it. Yeah, good question.
Thanks.
Yeah. Great. All right. Well, I'm gonna at least stop recording, but happy to